Hello everybody, welcome to the Learning Management System. I am Jabin Banu M. Nadaf, lecturer in Electrical and Electronics Engineering, Government Polytechnic, Belagavi. Dear all, today we are discussing one of the topic of Chapter 4 or Unit 4, Rectifiers and Filters. So in the previous session, we have had a discussion on the working of the center tap full wave rectifier. If we just have a quick glance on the center tap full wave rectifier, we have a center tap secondary of the transformer with the two diodes we had, diode D1 and diode D2, and the two ends of the diodes were connected to the load resistance and the center tap transformer. We also let us have a primary of the transformer. So in the positive half, this was a positive half cycle. In the positive half cycle, this end was positive, then this will be negative, this will be again positive, and this will be negative. So in this case, in the positive half cycles, we had D1 as forward bias. We all know what is forward biased. When the anode or the P is connected to positive terminal of the supply, cathode or N is connected to the negative terminal of the supply, the diode is said to be forward biased. So in our case, so this is the anode is positive, cathode is automatically the negative. So diode D1 will be forward biased. So if you see at the D2, so D2 is subjected to minus, the anode is subjected to the minus terminal and the cathode is subjected to the plus terminal. Therefore, D2 is reverse biased. So if the diode is forward biased, if the diode is forward biased, it acts like a closed switch. And if the diode is reverse biased, it acts like open switch. Okay, means the diode is off. Reverse bias andre diode off irutte. Off ಅಂದ ತಕ್ಷಣನೇ ನಾವು ಸ್ವಿಚ್ ಓಪನ್ ಇದೆನಾ ಈ ತರ ಅನ್ಕೋಬಹುದು. ಓಕೆ, ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಅಂತ ಹೇಳಿದ್ರೆ ಡಯೋಡ್ ಆನ್ ಆಗ್ತದೆ. ಆನ್ ಅಂದ ತಕ್ಷಣ ಡಯೋಡ್ ಕ್ಲೋಸ್ ಸ್ವಿಚ್ ತರ ಬಿಹೇವ್ ಆಗ್ತಾ ಇದೆ ಅಂತ ಮೀನಿಂಗ್. ಓಕೆ, ಸೊ if I represent them as a switches or just like a on. So if I draw like this, so this is on and it is connected to the secondary of the transformer. So here diode, this is a switch I will show here. Switch D1 is on, this is the load resistance, and I have a switch here, D2, it is off. It is off. Therefore, the current flows from P to Q. The current flows from P to Q, and this part of the input will be present at the output. So this is the load resistance, output load resistance. Therefore, this part of the input I will show here. Same, it is present. Okay, during the negative half cycle, if you see, we came to know that the diode D1 was reverse biased and diode D2 is forward bias. Now this part of the circuit will not work. This part of the circuit will work. The current flows from diode D2 to the center tap point. Again the current flows from P to Q. So the negative half cycle was present in the same direction. Therefore the output was coming in this way. What we studied in the center tap full wave rectifier. So we came to know that though we have at the input the bidirectional voltage, at the output we have a unidirectional output voltage. Unidirectional in the sense all the values of the voltage are above the zero axis. There is no minus direction, only plus values are there. Therefore it is a unidirectional voltage. So approximately we defined the rectifier and we have arrived at the definition of a rectifier by using the center tap full wave rectifier. So today similar type of operation we are studying and we are using the next version of the full wave rectifier, that is the bridge rectifier. So why we are going for the bridge rectifier is it is very difficult for us to design and to use the center tap transformer. Therefore, this is one of the disadvantage of the center tap full wave rectifier. Then also we have studied in the previous class that the diodes D1 are subjected to reverse voltage. If one diode is forward bias, another diode will be reverse biased. During the reverse bias of that particular diode, it is subjected to the reverse voltage. So the amount of reverse voltage is 2 times Vm. The peak inverse voltage of one diode will be 2 times Vm. So the peak inverse voltage also is a bit more. Therefore, we are eliminating the center tap full wave rectifier, and we are enhancing or improving the center tap full wave rectifier to a new type of rectifier. That itself is our today's topic, that is the bridge rectifier we are going to study in our today's class. So the working of the full wave bridge rectifier, then what is the average and the RMS value of the full wave and the bridge rectifier, what is the ripple factor and efficiency of the full wave bridge rectifier, and what are the advantages and disadvantages of full wave rectifier. These we are going to study. Okay, while studying this, so let us see what is the circuit diagram of the full wave bridge rectifier. So see, here we have 4 diodes. So diodes D1, diode D2, D3 and D4. They are arranged in a form of a bridge. And if you look carefully, so if you look at the M point, if you look at the M point, I have two cathodes connected together. See, this is the cathode. Cathode of the diode D1, cathode of the diode D2. Okay. Anyhow you connect, if you connect it in a form of a bridge, there are certain conditions where the load should be connected and where the supply should be connected. Okay. So at the M point, it is called as the common cathode point because two cathodes are joined together. Okay, at the M point. So at the L point, if you see, I have a common anode point. Common anode point because the anodes are connected together. If you look at the circuit diagram, see. So between the M and the L, we are connecting the load. In the sense that between the common cathode and the common anode point, we are connecting the load. Okay, usually this is the type of the circuit configuration. Wherever bridge wheel rectifiers are used, this type of configurations only will be used. Okay, and if you look at point A, so this is point A and this is point B. Okay, point A is connected to the secondary of the transformer and point B is also connected to the lower terminal of the secondary of the transformer. And if you look at the bridge, the cathode anode terminals are connected to the supply. Means what? The common anode and the common cathode point, between them load is connected, and between anode cathode or cathode anode points, supply will be connected. Okay, so this is the type of the configuration. So let us redraw the same circuit configuration. So let us redraw it here, just simple for your understanding. Okay, just redraw it here. Okay, so this is the supply. So this is A point, this is B point, this is B point, and this is okay, let it be. So here I will draw the rectifier. I will just first draw the load. So M I will draw, L I will draw. Okay, so this is common cathode point. Cathode, both cathodes are brought together. And this is common anode point. Both anodes will be brought together. See, both anodes are brought together and both cathodes are brought together. So I will call this D1, I will call this D2, I will call this D3, then I will call this D4. See, between the common cathode and common anode, I have the load connected, load resistance R. Then between the anode cathode, I will connect the supply. And I will just see what is the kind of output I am going to get. First, this is the input supply. Input supply is step down. So at points A and B also I will be getting the AC supply only, because it is a transformer. Its work is to transfer the voltage from one point to the another point. If the input is a AC, the out secondary of the transformer also will be the AC. So I will draw a AC supply. So 0. So I will write 180 degrees, then 360 degrees, etc. So from 0 to 180 degrees it is called positive half cycle, and from 180 to 360 degrees it is called as negative half cycle. This I will call it as V in or V input. So this is a positive half cycle and this is a negative half cycle. Okay, so what is happening in the positive half cycle and what is happening during the negative half cycle, this we are going to study. So if you look at the positive half cycle, then this A will be positive, B will be negative. So during the positive half cycle, if you look at during the positive half cycle of AC supply, A is positive with respect to B, we will tell. Instead of telling A is positive, B is negative, we will tell A is positive with respect to B. Andre A is positive, B is negative. Okay, so this positive is applied here, plus is applied here and minus is applied here. Now at the 4 diodes, so D1, then D2, then D3, then D4. What is happening to them? We have to study whether they are forward biased or whether they are reverse biased. We all know that if anode is plus, cathode is minus, the diode is forward biased. If anode is minus, cathode is plus, the diode is reverse biased. Okay, so anode. See here, so D1's anode, look at the D1's anode is plus. Okay, no need to look at the other side, just we will look D1's anode is plus, means what? D1 is forward bias. If you look at the D4 cathode is plus. If D4 cathode is plus, it means its anode is minus. So if the cathode is plus, it means that the diode is reverse biased. Means what? D4 is reverse biased. Carefully you look, correct agi nodri. Anode ge plus idre forward bias, cathode ge plus idre reverse bias. Okay, anode ge minus idrunu reverse bias, cathode ge minus idru forward bias. Okay, do not get confused. A is plus, so A of this is plus, it means that this is minus. Okay, so diode D1 is forward bias. Look at D2. So anode is minus, it means cathode will be plus. So anode is minus, cathode is plus, D2 is reverse bias. So D2 is reverse bias, D1 is forward bias. D1 is forward bias. Look at D3. Cathode is minus, anode is plus. So A plus K minus, D3 also will be forward bias. So D3 is forward bias. Look at D4. Cathode is plus, anode is minus. Cathode is plus, anode is minus, means diode is reverse bias. So D4 is reverse bias. So during the positive half cycle, so D1, D3 will be forward biased, then D2, D4 will be reverse bias. Okay, so here D1, D3 will be forward bias, means what? D1, D3 will be on, and D2, D4 will be off. D2, D4 will be off. It means that this is a open, D2 is a open switch, D4 is also a open switch. So ಅವೆರಡು ಯಾವುದು ಪಾತ್ರ ವಹಿಸೋದಿಲ್ಲ during the positive half cycle, which will be helping for the flow of the current. ಯಾವ ಪಾತ್ರ ವಹಿಸ್ತವೋ D1 and D3 will play a role in the flow of the current. So let us come up for our circuit diagram back. Okay, same circuit diagram I have drawn. See, let us come back. So D1, I came to know that D1 is forward biased, D3 is forward biased. Okay, so let us come. D2, D4, they are not working. So D2, D4 will not be helping for the flow of the current. So they will be off. So I will not show the diodes D2 and D4 because they are not helping for me for the flow of the current. So look at this one. See, D1 is on, D3 is on. So D2, D4 is off, D2 is also off. Therefore, I have not shown them. Okay. So how will be the current flows? The current will flow from A, then it flows to the anode of the diode D1, then it goes to M, then it flows through the load resistance RL, then it reaches the point L, then it flows to D3 and then it flows to D3, and from D3 it goes back to B. See, from A it flows, D1 it flows, load resistance it flows, D3 it flows and flows back to the negative of the supply. Therefore, during the positive half cycle of the input supply, so D1, D3 are forward biased and D2, D4 are reverse biased. Okay, so the current flows from A to D1 to M. From M, the current flows through L to the RL. From L, it flows to D3. Then it flows to B. So, how is the direction of the load current? So, the load current or the load voltage, load current ಅಂದ್ರೆ ಲೋಡ್ ಅಲ್ಲಿ ಫ್ಲೋ ಆಗುವಂತ ಕರೆಂಟ್, ಲೋಡ್ ವೋಲ್ಟೇಜ್, ಲೋಡ್ ಕಡೆ ಅಪಿಯರ್ ಆಗುವಂತ ವೋಲ್ಟೇಜ್. ಓಕೆ, ಸೊ ದ ಲೋಡ್ ಕರೆಂಟ್ ಆರ್ ದಿ ಲೋಡ್ ವೋಲ್ಟೇಜ್. ಓಕೆ, ವಾಟ್ ಈಸ್ ದ ಲೋಡ್? ಆರ್ ಎಲ್ ಈಸ್ ದಿ ಲೋಡ್. ಆರ್ ಎಲ್ ಒಳಗಡೆ ಕರೆಂಟ್ ಹೇಗೆ ಫ್ಲೋ ಆಗ್ತಾ ಇರುತ್ತೆ? ಇಟ್ ಈಸ್ ಫ್ರಮ್ ಎಂ ಟು ಎಲ್. ಓಕೆ, ದೆನ್ ಲೋಡ್ ವೋಲ್ಟೇಜ್ ಅಪಿಯರ್ ಯಾವ ತರ ಆಗ್ತದೆ? So we have plus here where the current enters, where the current leaves, it is the minus. So our V out will just be equal to V in. Why it is V in? Because this is also a closed switch. This is also a closed switch and this is just a line like this. Okay, this is also a current flows from M to L and back to the supply via the D3. So whatever present at the input, same will be reflected at the load. Let us go back to our session. So we discussed that if you look at the negative terminal of the supply, see if you look at the, okay, see here negative terminal, the same one I will represent now. Just for your information I am showing you. Okay, this is the secondary of the transformer. Idu A, idu B. Okay, so D1 is on. So D1 is on. D1 ee tara toristeni. Then load resistance I will show. Then D3 is on. D3 is on. On andre just close switch close agbittide. Then back to negative of the supply. See how is the current flowing? The current flows from A, then D1, then load resistance, then D3 back to the supply. See how it is looking? Whatever present here, in input present ಇರ್ತದಲ್ಲ, same will be reflected across the load. ಈ ತರ ಬೆಂಡ್ ಆಗೋ ಬದಲು ನಾ ಈ ತರ ತೋರಿಸಬಹುದು. I can show it in this way. See, secondary ಇದೆ, resistance ಇದೆ, ಎಲ್ಲ ತೆಗೆದುಬಿಟ್ಟು ಸೇಮೇ, both are same. See, just ಅದನ್ನ ಸರ್ಕ್ಯೂಟ್ ನ ಈ ತರ ಮಾಡಿಫೈ ಮಾಡಿದ್ದೇನೆ. ಅದರ ಅರ್ಥ ಏನಂದ್ರೆ, ಇಲ್ಲಿ ಏನ್ ಪಾಸಿಟಿವ್ ಹಾಫ್ ಸೈಕಲ್ ರಿಪೀಟ್ ಆಗ್ತಾ ಇದೆ, ಸೇಮ್ ಪಾಸಿಟಿವ್ ಹಾಫ್ ಸೈಕಲ್ ಇಲ್ಲಿ ಅವೈಲೇಬಲ್, ಇಟ್ ವಿಲ್ ಬಿ ಅವೈಲೇಬಲ್ ಹಿಯರ್. It will be. Why? Because the direction of the current is from M to L. So the load voltage V0, here at M it is plus and at L it is minus. This we have studied in our previous slide. Okay, in the slide ನಾವು ಈ ತರ ಸ್ಟಡಿ ಮಾಡಿದ್ವಿ. Okay, if you look at the output voltage, ಯಾವ ತರ ಡ್ರಾ ಮಾಡೋದು, how we will draw. So if I want to draw the output voltage, so in the positive half cycle, what is happening for me? In the positive half cycle, because D1, D3 are forward biased, all the positive half cycle will appear across the load. So all the input will be appearing across the load. So your positive half cycle output load resistance hatra ee tara output will be available for you. Idu yav tara kaantade? It is just resembling the positive half cycle. Okay, so now we will study what happens during the negative half cycle of our input. So during the negative half cycle, what is going to happen? During the negative half cycle of input voltage, during the negative half cycle of the input voltage, what is going to happen? Okay, so we will have A will be negative, B will be positive. So let us go back and see. Okay, let us go back and see. Okay, just we will for your simplicity, I see. So positive half cycle over, so negative half cycle is present. So negative half cycle means ee tara cycle, this will be present, means what? A will now be minus, B will be plus. A will be minus, B will be plus. Okay, so I will just show now what signs are available. Okay, we don't know, just I will show you now ಯಾವ ತರ sign available ಇರ್ತದೆ. Just I am removing this earlier signs. Okay, earlier signs ತೆಗಿತಾ ಇದ್ದೀನಿ. Okay, see. Okay, see now A is minus, B is plus. So let us look at diode D1. D1's anode is minus, cathode is plus. A minus, K plus, diode is reverse biased. So let us look at D2. D2 anode is plus, cathode is minus. Anode plus, cathode minus, D2 is forward biased. Let us look at D3. Okay, at D3, see, D3 cathode is plus, anode is minus. Anode minus, cathode plus, so D3 is reverse biased. Let us look at D4. Cathode is minus, automatically anode will be plus. Minus andre now plus and ankobeku. Okay, so D4 is forward biased. Okay, so in the negative half cycle of the input supply, if we see, D2, D4 is forward biased, D1, D3 are reverse biased. So in the negative half cycle, if you see, D2, D4 are forward biased, D1, D3 are reverse biased. Okay, So let us again draw the secondary of the transformer. Secondary of the transformer. So E and A, E and B. A is minus, B is plus. B is plus. So D2, D4 are forward biased. D1, D3 are reverse biased. Okay. So this is, so I will just draw M between M and the L. Mille L load ಬರೀತೇನೆ. So ಈ ಕಡೆ ಏನಿತ್ತು D4 ಇತ್ತು. Here was our D4. It is on. Okay. Here was our D2. It is also on. So D2 is on. D4 is on. D1 is off. D3 is off. See. This is the position. So now how the current flows. This is also important. Current flows plus in the minus flow ಆಗ್ತದೆ. From B it starts. Current flows from B. Okay. B it starts. B in the D2. D2 in the M. M in the L. L in the D4. See, from L to D4. D4 back to A. D4 back to A. See, the current was B was positive, A was negative. Current ಯಾವಾಗಲೂ positive in the negative flow ಆಗ್ತದೆ. So we mark the direction of the current from B to D2 to M to L to D4 and back to the negative of the supply. Okay. So the current was during the positive half cycle, the current in the secondary of the transformer was flowing from A to B. Okay. During the negative half cycle, the current in the secondary of the transformer is flowing from B to A. Okay. So it is by AC alva. For positive half cycle in the A to B flow ಆದರೆ negative half cycle ಅಲ್ಲಿ B to A flow ಆಗ್ತದೆ. Okay. But we are bothered about the load resistance. ನಮ್ದು load ಅಲ್ಲಿ ಯಾವ ತರ direction of current ಇದೆ. That is very, very important for us because we are talking of rectifiers. If you look at the load current of the rectifiers, it is flowing from M to L only. The load current is not at all changing its direction. Though the supply changed from A to B in the positive half cycle and in the negative half cycle, it obtained from B to A. Direction reverse ಆಯ್ತು ಇದರಲ್ಲಿ. ಎಲ್ಲೇ secondary of the transformer ಅಲ್ಲಿ reverse ಆಯ್ತು. But in the load ಅಲ್ಲಿ ಇದೆ M to L ಇದೆ. But in the load resistance, the direction of the current is from M to L only. It has not at all changed. M is positive only. L is negative only. In the positive half cycle also, look at the direction. It is from M to L only. M is positive and L is negative. In the negative half cycle also, the direction of the current is from M to L only. M is positive and L is negative. It means that this negative half cycle, the meaning of what I am telling is this negative half cycle, though it is minus reverse here, here the direction in the load, the direction is not at all changed. It is remaining plus only. It is remaining plus only. Therefore, the same negative half cycle has to remain plus for us. Therefore, it will be in this only, plus only. It will be positive only. So this happens when your D2, D4 are forward biased in the negative half cycle. See, though we have at the input side an alternating or a bidirectional voltage or current, at the output side we have a unidirectional output voltage or current. This itself is the definition of the rectifier which we have achieved with the help of a bridge type of a configuration. Okay, in the positive half cycle, D1, D3 will be forward biased and D2, D4 will be reverse biased. Therefore, we are getting the positive half cycle, and in the negative half cycle, D2, D4 will be forward biased. The same negative half cycle will be positive for us because the direction of the load current and the load voltage doesn't change in case of the bridge rectifier type of a configuration. So this is about the working of a bridge rectifier. See, in any of these cases, the direction of the current is not at all changing in the bridge rectifier. If you look at the negative half cycle, see, the current flows from B to D2, M to load resistance to L and back to the negative of the supply. And this procedure repeats. If you look at the waveform, see, in the positive half cycle, they have shown D1, D3 as forward bias, and in the negative half cycle, D2, D4 will be forward bias. Similarly, the voltage and similarly the will be the current. So we have just obtained the frequency of the rectifier is 2 times the supply frequency, and we always obtain that the output voltage of the rectifier always follows the input. So our output voltage, whatever these are present, we have the unidirectional voltage. ನಮಗೇನಿದೆ ಇಲ್ಲಿ unidirectional voltage means what? It is not having negative direction. All are the positive direction. It has the AC and the DC components. Okay. The waveform has a average DC value. Okay, the value of all the waveform is represented by a average value. That average value is known as a DC value, and since it is a unidirectional but it is instantaneous. Unidirectional ಇದೆ, 0 ಮೇಲ್ಗಡೆ ಇದೆ, correct, but ಅದು ಒಂದು ವ್ಯಾಲ್ಯೂ ಇಲ್ಲ, ಅದಕ್ಕೆ every time value change ಆಗ್ತಾ ಇದೆ, instantaneous ಇದೆ. Therefore we have the AC value which is given as the RMS value. Therefore a unidirectional voltage or such kind of waveform is said to be represented by its RMS value and the DC or the average value. So the average value, the average voltage for a full wave bridge rectifier is given by the formula 2Vm by pi, and current is given by the formula 2Im by pi. Similarly, the RMS value of the full wave bridge rectifier, the RMS voltage is given by Vm by root 2 and RMS current is given by Im by root 2. So we'll go on for the next topic. What is a ripple factor? If we talk of the rectifier, as I have already told, that the rectifier is a definition is nothing but a AC to DC. Somebody will be defining. DC means all values above 0 value. Okay, above 0. Then we can define bidirectional voltage or current to the unidirectional voltage or current. Unidirectional voltage or current is nothing again but the DC only. But if we talk of the regulated power supply node bitre, other DC this is a DC voltage. Fixed value 5 volts DC, 15 volts DC and other fixed value irtade. But we are not getting this type of DC here. We are getting this type of DC. Okay. It is said to have the many AC components which we have to remove, smoothen this wave to approximately this type of line. Okay. So that is meaning that we have to remove the AC components from the DC waveform. AC components we have to remove. How many components of AC are present, we don't know. But the presence of the AC components are called as the ripples in case of a bridge rectifier or any type of rectifier. So what is the definition of the ripple factor? The ratio of the RMS value of the AC component to the DC component of the output voltage or output current is known as ripple factor. So the ripple factor is given by the equation. Ripple factor is equal to the AC component of the output voltage or current to the DC component of the output voltage or current. We are talking only with respect to the output. So we have to see that we have to extract all the DC components from this waveform. It is having the majority of the AC component now, which we have to remove by a certain electronic circuits. But what is the measure of AC components present? That measure or how much AC is present, that measure or that value is given by the term ripple factor, which is defined as the ratio of RMS value of the AC component to the DC component of the rectified output, and it is denoted by the factor gamma. So the ripple factor is given by gamma. It is equal to IAC by IDC or IRMS, or it is VAC by VDC. Okay, so this C component is just given by this formula. See, it is given by this formula. Directly we are writing it by IRMS by IDC square minus 1. Okay, so it comes out to be in this way because our AC component is given by the root of IRMS square minus 1. It is given in this way. Okay, if I substitute this in the ripple factor, root of IRMS square minus 1, then divided by, instead of IDC, I will write like this, root of IDC square, If I take inside, it comes out to be root of IRMS by IDC square minus 1. Minus, it is IDC square. Okay, minus IDC square. If you take it inside, you will get it in this form. We know what IRMS is equal to IM by root 2 and IDC is equal to 2IM by pi. If I substitute this in the ripple factor equation, it is given by root of IRMS square. So IM by root 2 square divided by IDC square, 2IM by pi square, then minus 1. Okay, so if I again write it in this way, see, IM square by root 2 square is 2. IM square by 2 into 2IM square. 2 square is 4. IM square is IM square. Then divided by pi square minus 1. Minus. See, IM square will get cancels. This pi square will go in the numerator. So I will get gamma is equal to root of pi square by 2 4 it is 8 minus 1. If I solve this ripple factor of the full wave bridge rectifier, I will get it as 0.48. It means that approximately 48% of a AC component is present in a full wave bridge rectifier. So let's talk of the next definition. What is efficiency? Efficiency, we know efficiency always defined as the ratio of the output power to the input power. The output power is the DC power, input power is the AC power. So efficiency is equal to the output DC power divided by the input AC power. What is power? I square into R is the power. Okay, output current we have to take because DC power we are talking. Therefore, IEDC square, output resistance IDC square into RL. This is divided by AC. IRMS is the input current square into the resistance is RL plus the diode resistance. Small. Okay, IRD plus RL. If I substitute the value of IDC square, so it is 2IM by pi the whole square. 2IM by pi the whole square. And if I substitute the value of IRMS, it is IM by root 2 the whole square. Then into RL divided by RD plus RL. Okay, if I write like this, 4 IM square, I will write it here, 4 IM square divided by pi square into RL. This is the numerator part. Then denominator I will write IM square divided by root 2 square is 2. Root 2 square is 2 into RD plus RL. See, im square will get cancels. 2 will come in the numerator. It will become 8. 4 2 is 8. Pi square will remain pi square. Here, numerator is RL. Then denominator is RD plus RL. RD. If RD is very small as compared to RL, then it is neglected. Then it will become RL by RL. So RL will get cancels. What will remain for us? Only 8 upon pi square will remain for us. See, only 8 upon, if see here, if I see 8 divided by pi square. If RD is very much smaller, then it will become RL by RL, because RD is neglected. So it gets cancelled. If I find out the value of 8 by pi square and multiply by 100, the efficiency comes out to be 81.2%. Means what? Out of the 100% of the input power, 81.2% is the DC power. That is the meaning of this much of DC is extracted from 100% of AC. Okay. Yes. So this is about the terms and definitions related to the full wave bridge rectifier. Then also we studied about what is average value and the RMS value, and we studied the waveform also of the full wave bridge rectifier, and how is the working of the bridge rectifier in forward biasing positive half cycle, and the working of the full wave bridge rectifier in the negative half cycle. So some of the term, what is the peak inverse voltage? Already we have a discussion of the peak inverse voltage in half wave and center tap full wave rectifier. The meaning of the peak inverse voltage is, if a diode is reverse biased, what is the maximum reverse voltage that is present across the diode? That is the peak inverse voltage of the diode. Suppose we talk of a rectifier. Okay, so see here I will show the secondary of the transformer. Okay, so we came, the diode D1 was forward bias. Okay, diode D1 was forward bias, then load resistance, then diode D3 was forward bias. This was happening when? This was happening during the positive half cycle. So during the positive half cycle, D2 and D4 were not on. They were off because they were reverse biased. Reverse bias in the sense, the reverse voltage was applied. Here the plus voltage was applied. Here also the plus voltage was applied. Means here the positive voltage was applied. Here this positive voltage was applied here also. But here the reverse voltage was applied. This type of voltage, negative half cycle of the voltage was applied, minus negative half cycle of the voltage was applied. Is what? The diodes during the positive half cycle, which diodes were reverse biased? D2, D4 were reverse biased. If they are reverse biased, what was the maximum voltage applied across them? The negative peak of the input cycle. Input cycle is there. Positive half cycle is going on. So D1, D3 are on. They are happy enjoying that. But this D2, D4 are struggling because this negative half peak was available across them. This dotted I am showing now. This negative peak was available across them. What is the peak voltage? It is Vm. Therefore, the peak inverse voltage for the diode D2 and D4, because they are reverse biased, will be Vm minus Vm voltage Ra was applied across the diode. This much voltage the diode will be able to, or should be able to, withstand. Okay. Similarly, during the negative half cycle, okay, during the negative half cycle, D1, D3 were reverse bias. D2, D4 was forward bias. Which we have to reverse bias, that we have to be what is our important for us. Okay. Then if they are reverse bias, what is the maximum reverse voltage applied? Again, Vm is the maximum reverse voltage that can be applied. Therefore, in a full wave bridge rectifier, the PIV of the diodes is equal to Vm. What is Vm? The positive peak or the negative peak is called as the Vm. Okay. So what are the advantages and disadvantages of the full wave bridge rectifier? So here the center tap transformer is removed, and the PIV rating of the diode in the center tap circuit was 2 Vm. Here it is only Vm. Therefore, the PIV rating is half of that of the center tap full wave bridge rectifier, and the transformer size is much smaller as compared to the center tap transformer. And if and this bridge rectifier is available in the form of the packages, and it is suitable for high voltage applications. The disadvantage is only it has 4 diodes, and in each half cycle 2 diodes at a time will be working. Therefore, the on state drop due to or because of the resistance of the diode will be little bit more. Means the output voltage will be a very little bit less as compared to the center tap rectifier. So this is all about what we have discussed in the full wave bridge rectifiers. Here you can have a quick mind map or just a short form of what are the details of the full wave bridge rectifier. You can have a look over that. This is all about what I wanted to discuss in the today's class. Thank you one and all.